In this video, I'll go through the steps of hypothesis testing with an example. The first step is to identify the population and parameter of interest. Right now, we are interested in one mean or one proportion, but there are many different statistical tests, so this first step helps lead us to the appropriate one, which is the second step. All statistical tests have assumptions that must be met in order for test results to be valid. So once the test has been identified, we check assumptions for that test. The third step is to state the hypotheses. The next step is arguably the most important, and that is to build a model that represents the null hypothesis and determine what values will lead to its rejection. This model is a sampling distribution. We are now ready to collect data from a random or fair sample and to calculate a test statistic. Finally, we decide whether to reject the null hypothesis by comparing our statistic to the model. These steps are more of a guideline than rule of law, and we don't always follow them in this order, but they should give you some idea of the process of hypothesis testing. Now for an example. 30 years ago, researchers reported that 50% of all graduate students in the United States were physically fit. We are studying physical fitness and would like to see if this percentage has changed since then. We'll draw a random sample from the population of all graduate students currently at the University at Buffalo. The population of interest is all graduate students in the United States, and the parameter is the proportion who are physically fit. The appropriate test is the one-sample z-test. 3 assumptions must be met for this test. The first is random sampling, which we interpret as fair or unbiased. It is not always possible to draw a random sample, but in order to generalize to a population, the sample must represent this population in terms of the characteristics being measured. The observations must also be independent of one another. Knowing whether one member of the sample is physically fit should tell us nothing about whether another is. It also means that we are not measuring any subject more than once. One source calls this the unforgiving assumption, because if it is not met, we cannot carry out the procedure. Finally, the sample size must be relatively large, following our rule of thumb, because we are using the normal distribution as our model in place of the binomial. Let's check the assumptions for this study. The sample was not drawn from all graduate students in the U.S. Because we only have access to students at UB, we need to think of how this might limit our ability to generalize to the entire population. We're assessing physical fitness once for each subject, so the second assumption has been met. We need data to check the last assumption, so this is tabled for now. The null hypothesis is that the proportion of graduate students who are physically fit is 0.5, or that it is the same as it was 30 years ago. The research hypothesis is that the proportion is not 0.5. We are looking for a difference, so this is a two-tailed test. We can write these hypotheses in shorthand as p equals and does not equal 0.5. The model for the null hypothesis is the sampling distribution of p hat, with the parameters mu p hat and sigma p hat. We'll set the significance level at the standard value of 0.05. Plugging in our values for p and q, and the sample size of 100, we get a mean of 0.5 and a standard error of 0.05. Assuming that we have sufficient sample size, the model follows a normal distribution. We'll get one value for p hat from our sample, and then locate it on this distribution. We standardize the distribution so that the x-axis shows values of z instead of p hat. The significance level determines the rejection region. This is a two-tailed test, so alpha is divided equally into the two tails. The areas in the tails are called the rejection region. A test statistic that falls into the rejection region will lead us to reject the null hypothesis. The values for z that separate the region of rejection from the region of non-rejection are called the critical values of the test statistic. Using the table of normal probabilities, the value for z, such that the area above z is 0.025, is 1.96. The distribution is symmetric, so the value for z for a lower tail area is minus 1.96. We collect our data and find that 56% of the sample are physically fit. Is it reasonable to assume that the true proportion of graduate students who are physically fit is 0.5, given our data? Or do the data provide evidence against the null hypothesis? Let's find out. First, we need to check the last assumption, which has been met. In real life, we use a statistical program to do the calculations. These are the results from SPSS. Success is defined as yes, or physically fit, and the null hypothesis is that the proportion is equal to 0.5. Our sample statistic p-hat is equal to 0.56, and the difference between p-hat and mu p-hat is 0.06, and this is the standard error. Here is the z-test formula, which shows us how the test statistic was calculated. The last part of the table is the p-value. We did a two-tailed or two-sided test, so the p-value is 0.23. This is what the results look like on our model of the null hypothesis. Our test statistic is 1.2, and the area above 1.2 is 0.115. For any two-tailed test, the p-value is an area in both tails, so we multiply this number by 2 to get 0.23. What this tells us is that if we repeated the study, we would expect results at least this extreme nearly 1/4 of the time, when the null hypothesis is true. When we write these results, we indicate that the proportion of graduate students who are physically fit is not significantly different than 0.5. We add the statistical support for this statement at the end of the sentence. The z indicates that this was a z-test. We then indicate the sample size, calculated test statistic value, and p-value. Not statistically significantly different means that the null hypothesis was not rejected. If it had been rejected, we would have said that there was a statistically significant difference or effect. We could also say that the proportion of graduate students who are physically fit is not significantly different from research findings from 30 years ago. We never use the word prove because we can never prove anything with statistics. Our task is to determine whether the results provide evidence against the null hypothesis. To summarize, we start with the null hypothesis and then gather evidence against it. The process involves calculating a test statistic based on sample data, then comparing the p-value to our significance level. If the p-value is less than alpha, we reject the null hypothesis and conclude that the research hypothesis is a better model. Otherwise, we fail to reject it.